So, hello and welcome back to the third and final talk of the series on invariant theory of Hamiltonian mechanics and related numerical analysis by Oscar Cosserat from Göttingen University. Today he will talk on Hamiltonian Poisson integration. So, welcome Oscar, and over to you.
Yes, thank you. So hello everyone. So let me sum up what we have seen in the last two lectures. The first lecture was some basic properties of Hamiltonian flows on Poisson manifolds. And the message of the first lecture was that a naive approach to, or traditional approach to numerical analysis for such vector fields, to integrate such vector fields and to approximate their flow is not sufficient. And so in the second lecture, we have seen mathematical tools such as groupoids, for instance, and symplectic groupoids that allowed us to, provide ways to deal with the symplectic foliation of a Poisson manifold for the Hamiltonian trajectories. So in the first lecture, we have seen that traditional numerical methods could not perform well on Hamiltonian vector fields on a Poisson manifold because of this symplectic foliation, which is an invariant that is too rich and too subtle to be handled by traditional numerical methods. So the message of the lecture of last week was that symplectic groupoids are a nice tool to deal with symplectic foliation. In particular, we have used this Hamilton-Jacobi equation on a symplectic groupoid to observe that this Hamilton-Jacobi equation was helpful to approximate Hamiltonian trajectories by preserving the leaves of the symplectic foliation of a Poisson manifold. So what we're going to do today is to use this Hamilton-Jacobi equation to construct numerical methods that approximate Hamiltonian trajectories. So I will show a bunch of numerical simulations and a bit of the tools that we use to construct these numerics. In particular, Butcher series were used to compute formal solutions of the Hamilton-Jacobi equation. So the approximation of the solution of the Hamilton-Jacobi equation are computing through the Taylor series of the solution of the Hamilton-Jacobi equation. And these Taylor series are encoded by combinatorics that we will describe using Butcher series. Then the second part is a recipe to construct Hamiltonian Poisson integrators for any Hamiltonian system on a Poisson manifold once you have a birealization. So remember that one message of the last lecture was that also symplectic groupoids and birealizations are not so easy to compute explicitly in general. And then I will show two numerical simulations, two benchmarks of the numerics we we constructed. So the first numerical test will be around a singularity. So more precisely, we will compare the numerical simulations obtained through this Hamilton-Jacobi equation by a singularity, so a solution that explodes, and we will observe what's going on and compare different numerics. And the rigid body is a nice example to observe how good these numerical methods preserve the symmetries, and in particular the leaves of the symplectic foliation. So let's start. So the first definition of today is the definition of rooted trees. So let T be the set of non-planar trees defined as follows. A non-planar Butcher tree is a rooted tree defined recursively by this formula. So a rooted trees means it has a root here, right? So in the example below, the root is the dot below, and it's defined recursively by this operation. So if you have two trees, two rooted trees, you can always put them together by attaching them to a new root. So this is the recursive operation that defines the non-planar trees. And this notation, tau n dot tau 1 attached to the root, denotes this tree. So let me write tau n plugged to the root, and then again all the tau n minus 1 until tau 1 that are rooted also to the root. And so those are rooted trees, and we say that it's non-planar because we can flip them. So it's called non-planar because it's not attached to the plan. So imagine you can rotate them in the three-dimensional space. It's just a terminology, nothing bad. So non-planar means that the order of the branches does not matter. For instance, those two trees, so the first one is the flipped version of the other one. So those are rooted trees, and now we will use them to describe the Taylor series of the Hamilton-Jacobi equation. So we will construct the Taylor series of the solution of the Hamilton-Jacobi equation by some recursion operation. And this recursion is based on grafting. So the grafting of trees has this symbol, this arrow. The grafting of trees is defined as a product on T, on the space of rooted trees, non-planar rooted trees, returning the sum of all possibilities, counted with multiplicity, of grafting the root of one tree on the nodes of another tree. So here I give three examples. So in the first example, these three receive the tree with two nodes. So once grafted on the root and once grafted on the top node. And there are only two possibilities because the tree we graphed on had only two nodes. So in the next example, we graphed one node to the tree with three nodes. So there are three possibilities. So here we grafted on the root, and then we graphed on the top node, but it's the same if we graphed here and here, because the trees are non-planar. So that's why it's you get twice the same tree. And the third example is not so complicated, right? There's only one possibility because we graphed on the tree with one node. So this tree is here. So this is a product. We can extending this linearly on the free vector space generated by non-planar.
Oscar,
Yes.
so you are counting this in the second example.
Yes.
So when you crafted the vertex to, let's say, left edge and right edge of the tree here,
Yes.
so you are counting these two as a different grafting.
So you get this
Yes,
and this.
yes,
They are the
yes,
same because the trees are said to be non-planar.
right.
And so so what you get is this one plus this one plus this one, right? But you
Right.
have twice the same, so that's why there is a 2.
Yeah, so then in the first example,
Yes.
so I can graph the, let's say, the first one to the one that on the top and on the bottom. So on the top, the one that you got it, let's say, as a 4-path graph.
Yes.
And I can do on the bottom also to get the same thing. So why
Ah,
you did not consider here?
because the trees are rooted.
Yes.
Because the trees are rooted, so the you graft the root and not other nodes.
I see. Okay. 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 Understood. Thank you.
Yeah, sure. By extending the grafting product linearly on the free vector space generated by non-planar rooted trees, this defines the Prelli algebra of Butcher trees. So now I realize I won't define this word Prelli algebra. It's not so important anyway. You can check afterwards on the internet, but it's not central in this talk. Another remark is that a natural grading on the vector space T curved is given by the number of nodes and this grading behaves well with respect to the grafting. So now we want to relate these non-planar rooted trees to Hamilton-Jacobi equation. So let me come back just once to the Hamilton-Jacobi equation to show you, to remind you what this was. So this is the Hamilton-Jacobi equation for us. And the unknown is ST. Okay, and ST is a smooth function on M, the Poisson manifold. So what we will do is to compute the Taylor series of ST with respect to T. So the point of view we adopt here is to see ST as a formal series with respect to T. And then we will look for formal solutions of this Hamilton-Jacobi equation, where by formal, I mean Taylor series. So so we will look for some like this. So it's a Taylor series, so T to the power I over factorial I S I, where Si is a smooth function on M, right? This Taylor series has coefficients, smooth functions on M. So S0 equals 0, it means that, well, the zeros term will be 0. And a small exercise also is to observe that S1 equal H. So if you remember the axioms of a realization, now let us look at equation 2. So if you set T equals 0 on the left-hand side, where you will get S1. Oh, sorry. You will get S1. And on the right-hand side, if you fix T equals 0, then you will have dx of S0, which is 0. So you will get H composed with alpha composed with the 0 section. And if you remember the axioms of a birealization, alpha composed with 0 is the identity. So at the end, S1 equal H. So in a recent work with my co-author Adrien Laurent that I will mention further in the talk, we described S2, S3, and higher order terms by some formulas involving Poisson brackets, and those combinatoric formulas are underlying this part of the lecture. So this will be S2, for instance. So in order to encode the terms of the Hamilton-Jacobi equation, let me introduce the elementary differential map. So remember that G is a birealization. So G if we identify M with the zero section, then G is a tubular neighborhood of M inside T star M. And in particular, the cotangent projection might be restricted to G. So this we call P. And zero is the zero section of G. So it also comes from the cotangent bundle structure. And it corresponds with the identity section of the symplectic groupoid. Let H a Hamiltonian. Then the elementary differential map FH from T to smooth functions on M associated to H is defined recursively again by the following. So F of the root equals H. So this is reminiscent of the fact that S1 equal H that we have seen a few minutes ago. And then we want to compute higher terms. So this is recursive again. And here the Poisson bracket that I indexed by omega is the Poisson bracket of the symplectic form on the cotangent bundle. And the idea is to compute the terms of the Taylor series of the Hamilton-Jacobi equation by grafting trees and apply f of h. Right, so the Taylor series of the solution of the Hamilton-Jacobi equation will actually be a Butcher series. So let me explain what the Butcher series is. The B series associated to H, to the Hamiltonian H, is the following formal series indexed by a coefficient map A in T star. So what is T star? So A, so T stars are characters on T. So I mean linear map going from T to R. So this is the formula for the Butcher series. And you may observe that f of th is indeed a formal series. So this is well defined. So all of this, for all of this Butcher series, there is a nice book which is quite known in the domain of geometric integrators. It's called Geometric Numerical Integration. And there are plenty of explanations there about Butcher series. So now let me come to the result we wanted for. So this lemma is if you want to try to compute it by yourself. Otherwise, let me state the theorem. Let ST be the solution of the Hamilton-Jacobi equation. Then its Taylor expansion is given by the Butcher series associated with this character, E, where E is recursively defined as follows. So that's very nice because you see, if you have an ordinary differential equation, you might always try to look at the solution x of t by looking at the Taylor series of x of t with respect to t, and try to make this series converge for small t, something like this. But for Poisson Hamiltonian systems, if you truncate the Taylor series of this ordinary differential equation naively, it does not work. It will destroy the symplectic foliation. While if you lift up this Hamiltonian vector field to the symplectic groupoid, and then you look at the Taylor series of this Hamilton-Jacobi solution, well, there it will provide some satisfying approximation of the dynamical system. So somehow the symplectic groupoid was a nice framework to construct numerical methods in Poisson geometry. So let me give an explicit construction through B realizations. So you start with the Poisson structure on RD. You assume that the B realization alpha beta is constructed for P. So I said it several times, but still let me repeat that this assumption is not for free. It's hard in general to construct a B realization. I know how to construct some for families of examples, but if you give me a generic Poisson structure, there are ways to approximate the construction of the symplectic groupoid, but it's still a field of research to construct symplectic groupoids for Poisson structures. It's been done formally, for instance, but it's a complicated question. I'm not answering right now. So let us assume we have a B realization for the Poisson structure pi, and let H a Hamiltonian. So here everything is in coordinates. Oh, there is a typo here. D and, well, it's D here, sorry. Everything is in coordinates because when you do numerical analysis, at some point you have to implement something on your computer, and this will be in coordinates. It's possible to handle manifolds, even intrinsic manifolds with a computer by implementing charts, etc. But this is not a question we raise here. So let us remain in coordinates to describe the implementation. So step 1, solve the Hamilton-Jacobi equation up to order k using Butcher series of equation 5. So the theorem I just stated with my co-author, allows to construct any solution at any order of the Hamilton-Jacobi equation. So what you do if you want to construct an integrator of order k is that you truncate this Taylor series at order k, and you obtain S k of delta t being the time step. Right, and it's no longer a formal series because we truncated the formal series, so we are left with a finite number of terms, and this finite number of terms becomes a smooth function while we specify the time step delta t being fixed and small enough. Let xn in Rd, so xn will be the point we want to iterate. Solve the nonlinear equation alpha xn bar gradient of sk delta t at xn bar equal xn. So that's where you need delta t to be small enough, because it follows from implicit function theorem or inverse function theorem that for delta t small enough, this equation has a solution. So in particular, for delta t equals 0, remember that S0 equals 0 and alpha at the 0 section is the identity. So if delta t equals 0, then what you get for xn bar is xn. This is one of the points of this equation. The other point of this equation, so using inverse function theorem, you obtain that for delta t small enough, this is solvable. So in practice, you may solve this by fixed point method like Newton descent. It converges quite fast because the map alpha has nice geometric properties. Remember that in the symplectic groupoid, in the B realization, say. Well, one of the nice geometric features of alpha is that the fibers of alpha are transverse to the identity section, and that makes the Newton descent converging quite fast. That's nice. So you solve this, you obtain xn bar, and then the last step is then given by xn plus 1 equal beta xn bar gradient of sk delta t xn bar. And this last step is explicit once you know beta, right? Beta is given because the B realization is given. So this last step is explicit. The step 2 is implicit. You have to solve a nonlinear equation, which is not so hard to solve. But that's a general comment in numerical analysis in general, that if you want your numerical method to preserve something, or if you want your numerical method to have some nice geometric features, generically speaking, your numerical method will be implicit. It's very unlikely for a geometric numerical method to be explicit, and that's more or less the price to pay. If you want a nice numerical method in general, the integrator will become a bit more complicated, a bit more involved than something basic and traditional. So what can we expect from the numerical behavior of this numerical method. First point, it will stay on a leaf because the numerical methods are induced by bisections. Remember that in the last lecture, we have seen that any Lie groupoid induces foliation on the base. And if you pick a bisection of your Lie groupoid, it induces a diffeomorphism on the base that remains on a leaf. Like iterations of this diffeomorphism will remain on one leaf. And that's exactly how we constructed our numerical method. So we expect this numerics to stay on a leaf. The second remark is a bit more involved or a bit more informal. We expect this numerical method to be stable near a singularity because these bisections are Lagrangian. What is meant here is that since these bisections are Lagrangian, the diffeomorphism on the base will preserve the Poisson structure, and it is observed for decades now that at least in the symplectic case, preserving the symplectic structure provides some stability for the numerical method. And we also hope those integrators to oscillate around first integrals. Again, this is exactly what symplectic integrators do. So I will, this last remark, I will precise in a minute. So we will see right now benchmarks of numerics. So I will explain in this numerics what do I mean by oscillating around first integrals. So we had three examples of Poisson structures in the first lecture. Remember that we had the symplectic, we had the symplectic, the Poisson structure coming from the symplectic form, and we also had the Lie Poisson structure. So it was a linear Poisson structures, and an example of a quadratic Poisson structure that was called the cluster Poisson structure. So let me start with the third example of the first lecture. So the example of a cluster Poisson structure on R3. So I recall the Poisson bracket, which is indeed quadratic. So the components of the bivector are quadratic. This is a formula for realization, so the map alpha and beta. And here I pictured a symplectic leaf. And remember that an example of a Hamiltonian system I gave for this cluster Poisson structure is provided by h of x equals the sum of xi. And then we obtain this Lotka-Volterra dynamical system. And it's very nice for us to have this Lotka-Volterra dynamical system because we can compare the dynamics of our discrete trajectory with the real trajectory of this dynamical system. So this equation has been solved by Paul Van Eyck and his collaborators about 10 years ago. And we know that it explodes when t goes to infinity. It explodes exponentially fast, as pictured in this curve. So Z is x3 actually. So you see that it's very close to 0, but then x1 being x goes to minus infinity, and x2 being y on this picture runs into infinity. And so we have an analytic expression for the solution. And so you may pick any numerics you want and compare it with the real trajectory to observe how good you are, or what error do you do. So what we have done is to compare the Poisson, the numerics obtained by the Hamilton-Jacobi equation with a traditional method. So the traditional method is Runge-Kutta of second order. And we compare this with the Hamilton-Jacobi equation of the Hamilton-Jacobi integrators of first order. So let me show you the results. So here we plotted the distance to the real trajectory. And with respect to the number of iterations, well, the number of iterations with respect to the distance to the real trajectory. And what we see is, so the Poisson, the Hamiltonian Poisson integrator is of order 1. The Runge-Kutta method is of order 2, but still the Hamiltonian Poisson integrator is more faithful to the real trajectory. So everything explodes. So this is normal. If a quantity goes to infinity, whatever your numerics will be, it will explode anyway. So your computer cannot quite handle two big numbers. But before it's exploding, the Hamiltonian Poisson integrator remains quite close to the real trajectory. At least it remains closer to the real trajectory than the Runge-Kutta method, even though the Runge-Kutta method is of order 2, while the Hamiltonian Poisson integrator we used is of order 1. So this is what I meant by some stability is expected for our numerics. It's more likely that you obtain more stable methods if those methods preserve the geometrical invariance of your dynamical system. So let me come here with my second example. So I recall the Poisson bracket. Here you see that the Poisson bracket is linear. Coefficients vanish at 0. They are of order 1. This is a formula for the realization with the map alpha and beta. And I recall the symplectic foliation of this Poisson bracket, which is made by sphere. So you can think about this symplectic foliation as R3 foliated by spheres with various radius. And don't forget the singularity in the middle. So this is the Hamiltonian system we care about right now. It's called the angular velocity of a rigid body in R3. Or angular momentum, maybe, depending on the factor you put. You see that the trajectory is periodic. So this is a real trajectory. So all of those examples are toy examples where we actually know what's going on and we want to compare existing numerics on those examples. So it's important that we know how to solve or how those systems behave so that we can benchmark, compare the new numerical methods we obtained. And here we know that the trajectory is periodic. Let me explain you briefly why this trajectory is periodic. It's periodic because there are two conserved quantities. One of them is the Hamiltonian. Of course, the Hamiltonian is the first integral of itself. Remember, from the first lecture, this one comes from the antisymmetry of the Poisson bracket. And the linear the momentum of the velocity is preserved as well. I can even sketch, maybe I can make a picture. So you see that H is a polynomial of degree 2. It's homogeneous of degree 2. So the levels of H will be ellipsoids. And so this is for H. And the second first integral, sometimes it's written I, is given by the norm, where the square of the norm of X. Meaning that the second first integral has levels that are given by a sphere. So my picture won't be very good anyway. You see that this ellipsoid and this sphere meet at a periodic orbit. So this is one way to prove that the orbit will be periodic. It's because you have two quantities that are preserved and your spaces of dimension 3. So what remains is just something of dimension 1. And since everything is compact, the curve is periodic. So the periodicity is nice because now we can ask which numerics will preserve the periodicity of the curve. It's not so easy in general to preserve the periodicity of a curve because on the long run, if you do many iterations, the errors of your numerical methods will accumulate and you will eventually run away from this periodic trajectory you try to approximate. So this is the first numerical simulation that says that the Hamiltonian Poisson integrator of order 2 preserves Casimir levels, while the Runge-Kutta method of order 4 does not preserve those Casimirs at all. So what does it mean to preserve the Casimirs? The Casimirs here means to remain on a symplectic leaf. So we see that the Hamiltonian Poisson integrator of order 2 completely preserves the Casimir, while the Runge-Kutta method run away linearly on time. So what? Let me tell you again what it means if I come back to the picture. For the Runge-Kutta method, if you start at a point on the sphere, it means that eventually you will run away from the sphere and run to infinity, while the Hamiltonian trajectory is supposed to remain on the sphere. So that was for the symplectic foliation, for the symplectic leaves. And now let us check the preservation of the Hamiltonian levels. So on the left, the Runge-Kutta method of order 4 completely explodes the Hamiltonian values as well. So don't forget that the scale here is logarithmic. So the explosion is linear with respect to time, actually. And on the right, we see that the Hamiltonian Poisson integrator of order 2 oscillates around the Hamiltonian levels. So it's kind of magic. Let me come back to the periodic orbit. It means that actually, while the Runge-Kutta method of order 4 runs away at infinity when the number of iteration grows, the Hamiltonian Poisson integrator we computed will oscillate around the periodic orbit. So it's not periodic here. It's not necessarily, it does not necessarily match the point we started with, but still it will oscillate on the long run and keep on oscillating around the periodic trajectory. And the amplitudes of this oscillation are controlled by the order of the method. So they are not controlled by the time step. The time step does not really matter actually in this story. They are controlled by the order of the method. So if you want to reduce the amplitude of these oscillations, you may pick a higher order method using those Butcher series I showed you before, for example. So that was the meaning of those oscillations. So I'm about to finish. This is exercises if you want to try, and some bibliography for the third lecture. So these are 2 articles. The first one is an article I wrote with my PhD advisors during my PhD, where we implement and observe the behavior of those Hamiltonian Poisson integrators. And this is an article, well, it's a preprint for now, where we explain how to solve the Hamilton-Jacobi equation. I have 2 perspectives, so I keep on working on this Hamiltonian Poisson integrators. one model I work on is the Timoshenko model. The Timoshenko model is a model in solid mechanics where it modelizes the deformation of a beam. So it modelizes the deformation of some solid with rigidity assumptions. And this model is Hamiltonian, so there is a preprint here which is called Timoshenko beam under finite and dynamic transformations that I wrote with my co-author Loïc Lemarec, where we investigated the Hamiltonian structures of the Timoshenko model, and we're working right now on constructing numerical methods that are adapted to these Hamiltonian structures. And we expect this numerical method to track periodic orbits efficiently or detect instabilities, for instance. And this is a second perspective. So I spoke about some perspective in solid mechanics, but there are also Hamiltonian equations that are interesting in plasma physics for Vlasov-Maxwell equation. We try to see how to implement those numerics there. So those two perspectives I gave you about solid mechanics and plasma physics are actually much harder than what I've been teaching in this lecture, because those equations are partial differential equations with the Hamiltonian structures, and the numerics for PDEs is well, to me it's much harder than numerics for ODEs, such as examples I gave in this lecture. And the last perspective I would like to mention is the construction of viralizations by studying deformation theory of symplectic groupoids. So those are ways to compute or approximate alpha and beta for a given Poisson structure. And this requires some algebraic tools that we don't fully understand yet, but we're working on it. So I'm done for today.
Okay, thank you, Oscar. Thank you for the nice talk. Really explicit some competition, numerical comparison between the known methods. So, Sachin, do you have any question?
No, I don't have.
So I just have a like naive question, kind of not question, just query kind of thing. So, like in the past, how do you compare the Hamiltonian Poisson integrators and the Runge-Kutta method of order 2? Like, what about the order 4 thing? Yeah, here. Yeah.
Here,
Yeah.
if I pick a Runge-Kutta method of order 14,
Yeah, like the comparison still remains like this similar thing. Like it seems the Rangagutta method of order 4 is more accurate than the order 2 thing. So like the comparison remains same, or it like goes uh, wrong after like more time kind of thing.
yes, the Runge-Kutta method of order 14 would do better than the Runge-Kutta method of order 2.
True. Yeah.
So I've been thinking about this example also. The thing is, at some point, what happens, so since everything runs to infinity, so keep in mind that the Runge-Kutta methods are explicit. They're just additions and multiplications of numbers, while for this Poisson integrator, you have to solve a nonlinear equation at every iteration.
Right.
So at some point, this nonlinear, this solving of a nonlinear equation starts to mess up if you run to infinity. At some point, at some point everything starts to mess up. So it may happen. So I don't know. But so I stopped this simulation at the right time. But then if you keep on, see that
It will also go up here, right?
The green trajectory of the discrete trajectory of the Poisson integrator also explodes, of course.
Yeah. That's what you told me. Previous example kind of thing, like x1 t, x2 to t, those also goes to infinity at that time.
Right. So the trajectory itself goes to infinity, but also the distance between the integrator and the real trajectory also goes to infinity, because
Right.
you cannot approximate anything anymore. Numbers are too big.
Okay. Thank you. So that's I don't have any other questions. So so let's thank then Oscar. Really nice presentation and talks. Thanks for the talks. Thank you then.
You're welcome.
Then let's stop here.